Yes, EQTM, that's the one example we saw from the homework, and I think it's one of the nicest examples because EQ is kind of a crazy language, and it's fairly easy to see why that thing would not be recognizable. And then its complement is even messier than that. So that's an example of a language and its complement both being very much unrecognizable. Okay. F, if a language is decidable, then its complement must be Turing recognizable. True. Why? If we have a language A that's decidable, what do we know about its complement? Yes, it's also decidable. Decidable, again, is kind of the easiest of these languages to deal with because we know that we can run, or we know that there's a machine on which we can do a check, and we know it's always going to return true or false. It's never going to loop forever. So all we have to do is to build a decider for the complement is to just use that same decider, but then just negate the result. Flip the true to false, the false to true. Just return not whatever the other decider did. And that's also going to loop for it. Well, that's also never going to loop forever. So that's also going to be a decider, but it's going to be a decider for the complement. And of course, all deciders or all languages that are decidable are, of course, recognizable because a decider is a much more restrictive form of recognizer. Again, recognizable if there's a recognizer for it. And a recognizer it returns true on the true cases, but on the negative cases, it either will return false or loop forever. Deciders do that, but deciders also have the additional constraint that it will never loop forever. So in the negative cases, it will always return false. It will always terminate. It will always halt. Okay? Okay. Problem 2. Find the discussion from the lectures. Suppose we have the following program here. Now, this SumFun program takes pairs. It takes a machine encoding and an input W, and it runs the machine on the encoding, or it runs the machine on the input using the UTM. And if it returns a value, true or false, then what it will do is it will return the negation of that. So it'll flip the trues to falses and the falses to true. So first question, is this program a decider, a recognizer, or both? Yes, it is a recognizer, but it is not a decider. Why is it not a recognizer? Why is it not a decider? Right. This is going to be problematic if M loops forever on W. Because remember, the universal Turing machine does exactly what would happen if we run M on W. So if M loops forever on W, UTM on this MW encoding here is going to loop forever. And because this program has some inputs for which it may loop forever, this program here cannot be a decider. It is a recognizer because it returns true or false. Well, actually, it can return true or false, and it may loop forever. So therefore, it does recognize a language. If it did some other bizarre thing, like convert one thing into another and start returning strings of some other sort, then this thing would be really more of a transducer, sort of a converter of one thing or one string into another. But since this is just returning trues and falses, this thing is a recognizer. Okay? Okay, so question, what language does this thing recognize? Yeah, well, first off, we know that because we are doing this here, we're negating whatever the UTM gives out. We know that the only times in which this thing here is going to return true is if this is false. So we know that all the elements here for which this returns true, these will have to be in ATM complement. However, there's a catch here. There's some elements of ATM complement that are going to cause problems for this, or that this thing will not actually return true for? What are those pairs? What's going on with those? Right. The thing is that if M loops forever on W, guess what? We're never going to get here. We're never going to be able to return anything in those cases. So those strings, those encodings are not recognized by this. Again, looping forever is considered a negative case. So it's not this per se, but what we have to do is we have to look at the cases where there are things in ATM complement, but it is those cases on which the machine does halt on the input. It does have to return. It has to return a false specifically. So the actual language that it recognizes is this right here. It's all the cases on which M on input W halts, but is an ATM complement. So what this boils down to is these are all the pairs on which M rejects W. That's what this is here. That's what this set is. Okay? Okay. What? Yes, this is the only answer. Yes. Okay, because you mean for this here? Are you saying why it's not this?
Sorry, did you ask something?
Someone, hold on, Hans. Someone in the audience is asking something. I'm trying to hear what he's saying. Could you please?
He must type. I hear nothing.
Hans, please, Hans. Please say that again.
Yeah. No, I thought that you asked me something.
No.
But anyway, if a student asks something, he must type because I hear nothing of the student.
Okay. Okay. Please start again. Not you, Hans.